are now getting into chapter 3. So 1 down, 2 down, now we're on the 3rd one. And this is probably one of my favorite chapters, though they're all really good. But this one's fun. There's going to be a lot of experiments. And this is all about sensation and perception. So you might have known of sensation being our senses. So if we can touch things, if we can smell things, if we can hear things, if we can see things. And then there might be a few senses you didn't really realize you had. Because I can tell you right now, there's more than 5. But just what are senses and how does that vary from something known as perception? That is what we're going to be talking about in this chapter. But in the beginning, we are going to be talking about just sensation. What sensation is, again. And when you hear sensation, think your senses. And in this video, we're going to talk about senses as a whole, and then we're going to go into vision. And then after vision, in the other videos, we're going to start going through some of the other senses, and some that you might not have known about. What do we mean by sensation? What is a sensation? When you're having a sensation, what does that truly mean? At least as far as psychology describes it. And then we're going to talk about things about just how minor can a sense be that we can still sense it. Well, I get ahead of myself. So when we say sensation, for the sake of this class, and for the sake of your exam, it is the process by which we receive, transform, and process stimuli from our external world to create a sensory experience. That's a mouthful. Essentially, what that is saying is it's all of the information outside of our bodies coming in. And so I mentioned this in the previous chapter, that if we didn't have our senses, if none of our senses worked, hearing, seeing, smelling, we would be shut off from the world. There'd be no way of information making it in. We can only see the world around us or hear the world around us or just experience real life through our senses. And so that's essentially what this is saying. It's just taking that information in. And then we have a sensory experience. So in this, we're looking at a picture of flowers. So how that information comes in. When we have candy and we taste it. Sorry, I still have candy canes from Christmas. When we're tasting something, tasting that sweetness, that's an experience of the outside world making its way in. So that's what we mean by sensation. And again, for the sake of this class, it's probably more wordy than it needs to be, but it's the process by which we're receiving, transforming, and processing stimuli. Again, stimuli is just stuff happening. Stimuli from our external world to create a sensory experience. So it's just the outside world finding a way to communicate with us. And in regards to sensation, we have what's known as the absolute threshold. What this means is essentially we can detect this sense 50% of the time. If it's any less than 50%, that means the majority of the time we don't sense it. And so the majority of the time it's kind of, don't know if I felt anything. And then if it's more than 50% of the time, it's okay, we can definitely, sense it. We want to get the bare minimum of the senses. And so that's what we mean by absolute threshold. It's the smallest amount of a sense that we can still sense. And don't ask me how scientists figure this out. And we're going to be testing one of these. I'm going to make a video with all the different experiments, so don't worry. We're going to be testing one of these. So the first one's sight. And so it's seeing a candle flame 30 miles away on a clear night. So the idea is that if you're on a nice straight road, nice clear evening, and you have a candle lit 30 miles away, a person 50% of the time could say, yeah, I think I see it. Any less, the majority wouldn't see it. Any more, and it's not quite there to the threshold. For hearing, it's hearing a watch ticking 20 feet away. Again, in an absolute quiet environment. Touch, again, don't ask me how scientists figure this one out, but it's the feeling of a bee's wing falling a distance of 1 centimeter onto the cheek. And if you ever want to test your sense of touch, a lot of times people don't realize just how sensitive it is. If you ever put your hand on a surface, you can feel, even if there's a single grain of sand You can feel that it's there. You can feel that bump. Sometimes we don't realize just how sensitive our sense of touch is. But that's why, bee's wing falling from a centimeter. Smell is a 1 drop of perfume in a 3-room house. Sorry. Again, they don't really specify what type of perfume because there's some really strong ones out there. But probably just kind of a mainstream perfume. Again, it'd be a very, very faint smell. And then taste is 1 teaspoon of sugar dissolved in 2 gallons of water. 2 gallons of water is a big gallon. But the idea is, again, a single teaspoon, 50% of the time, people would be like, oh yeah, it smells sweet. But again, we're going to be testing one of these to see if that's the absolute threshold later on, where we will continue. And these are all examples of absolute threshold. We also have something known as the difference threshold. And this is a little different. The way to remember this is the minimal difference between 2 stimulus. So 2 things that look almost identical, but they're just a little bit different. So much so that, again, 50% of the time you can say, that's different. Classic example, by the way, is Coca-Cola. Some of you might not have realized it, but they changed the way their cans look. It used to look like this, where it had, a little bit more splotchy dots and then a little yellow thing. Now it's kind of more basic, probably because, it saves money on color, which makes sense. But the majority of it looks the same, and so chances are a lot of people didn't realize that it changed, because for the most part, just at a glance, they look the same. This is the just noticeable difference, when you can tell that something's a little different. But yeah, so just like the absolute threshold, the difference threshold, it's that 50% of the time. Because again, any less, then it means the majority didn't notice it. Any more, and you're not quite there to the threshold. So that 50% is that crucial thing. And I know for a fact that on your first exam, there will be questions about both the absolute threshold and the difference threshold. So the thing to remember, difference threshold, that bare minimum of noticing the difference. Whereas absolute threshold is that just able to notice it. It doesn't have to be a difference, it's just noticing that it's there 50% of the time. Alright, another thing that I know is on your first exam is we have, for all of our senses, again, your sensation is all about taking information from the outside world and bringing it into our bodies. How do we do that? It's not just gaping holes, though sometimes it is. But we have these things known as sensory receptors. They are what receive that information in our senses. So sensory receptors. And some examples are the rods and cones in your eyes. We're going to talk about that very quickly, or very soon, when we talk about the eyes and vision and how that works very shortly. We also have hair cells in your inner ears. That will be the next module. When we talk about hearing and just how hearing works. We actually have teeny little hairs, and they're the ones that bring in that information from the outside world. This is very important because a lot of people miss it on the first exam, so pay attention. On the tongue, we have taste cells, not taste buds, though we do have taste buds, but the specific sensory receptors are taste cells that actually are on the taste buds. We're also going to be doing an experiment that messes with taste and kind of how taste works. But again, I get ahead of myself. And then we have receptor cells in the upper nostrils. So some of you might not know, but when we are smelling things, it's actually chemicals. And they interact with these different receptors. And then the last thing are the nerve endings in the skin. We talked about nerves, again, in the last chapter. We talked about, nerve endings and nerve cells and the different neurons and the way they communicate. I've talked about how a lot of the nerve endings on my fingers I don't feel anymore because of being a not-so-good cook. I've sliced my fingers quite a few times. And because I've sliced my fingers, I have cut those nerve endings. And so I don't feel it anymore. I can't get that information in from the outside world anymore, at least on my fingers. But these are just some of the examples of the sensory receptors for the 5 senses. Remember, there's more than 5. But I got ahead of myself again. We also have something known as sensory adaptation. So it's turning down the volume, as it says on here. And it's when our senses, again, get turned down. We can still feel it, we can still sense it, but not as intensely as we did when we first experienced it. Classic example, if you've ever gone into a pool, or let's say you've taken a shower and it's a cold shower. We all hate that, except for those people that take the cold showers. I don't think they do. So let's say, that right now it's the middle of winter, but let's say that, you want to jump in the pool. You've gone down to Florida, so it's warmer, but it's still winter time, so it's not that warm. The water is still a bit cold. So, you get yourself all hyped up, you got your trunks on, you go and you jump in the water, and it's cold. But then, after a while you swim around a little bit and you're like, oh, you know what, it's actually not that bad. I can survive this. Well, when you first jumped in, it was really, really cold. Now, it doesn't feel that bad. It's not that your body heated up the water, though I wish it was that easy, because, man, some of those pools are cold. Well, what happened is your senses adapted to that cold. So you can still feel that it's cold, you can still feel that you're in water, but it doesn't feel as bad. And this is sensory adaptation. So again, over time, your system becomes less sensitive to it because it's an unchanging stimulus. This is a little different from something known as habituation, which you don't need to know in this class, but it's important, to me to know the difference. Habituation is when you completely stop sensing it at all. And so an example of this is if you've ever gone into a room, let's say that someone cuts the cheese, and it's really smelly at first, but then you actually realize it after 5-10 minutes, you're like, I don't smell it anymore. Or you go into a place that has a really, really powerful perfume, and then after a while you're like, I don't smell it anymore. That is habituation. You don't smell it at all. But sensory adaptation, you can still feel it, you can still sense it. It's just been turned down a little. Another example is people that put creamers in their coffee. After a while, you might start putting more and more creamer in it. Because, when you used to have just one teeny little thing of creamer, you could taste that sweetness, but then you kind of get used to that sweetness, so you have to add more and more to get that nice sweetness. That's sensory adaptation. So it's any of your senses where, after a while, okay, for me, listening to music. I find that if I don't have my volume cranked up, all the way, I'll find myself over time turning the volume up a little more and a little more and a little more, because I get used to how loud it is, and I just want it more intense. So I've adapted to it. I can still hear the music, obviously, but it doesn't feel as intense, it doesn't feel as loud. Could also be that I'm damaging my ear, which we will be talking about in the next module, the module after. So speaking of the next module, we're now going to talk about vision. And I'm just going to go ahead and go straight into this module because, well, essentially I'm too lazy to stop and re-record myself and I'm on a roll. So now we're going to talk about one of the senses in particular, which is vision. Because vision is really interesting. It's also a very important sense because, again, a lot of times how you're learning right now, though also auditory, which is why hearing's next. But you're seeing me, talk and wave my hands around like a crazy person. You're seeing the notes up on this slide. It's probably doing that obnoxious thing where there's little lines going, which, by the way, has to do with how our vision works, but that's in way more detail. Take a physics class. But vision is very interesting. It's seeing light. But how does it work? When we see stuff, we see it in what we call essentially, well, it's our vision, which is the colors of essentially from a magenta-y red to a purpley. But these are all the different wavelengths that we know about for the most part, as they go from very, very quick wavelengths to very, very slow wavelengths. And so you have things like radio and television waves, you have microwaves, you have infrared, which now, thanks to technology, we can see. In fact, the camera I'm using right now to record this can do infrared, which means I can go ghost hunting. But I get off topic. And then you have things like X-rays, gamma rays, cosmic rays. But what we can see, this little bit right here, that's it. There's some animals out there that can see far more. There's some that can see into, the infrared, ultraviolet, all that. But for us, in this little area right here, it's our kind of visual range, as it But now that we know the range, how does it work? This is our wonderful eye. It is very, very detailed. And there's many different parts. Again, you will not need to have it memorized per se, but it is important to know the different parts. And I'm essentially going to explain it by going through the steps. So we start with the light. This is the light, and it's coming in to your eye. The first thing it hits is this out here. This is the cornea. It's that clear thing. You can see it more on like a cat's eye. If you kind of look at their eye on the side, you kind of see this clear film over top of it. So this helps to protect the eye. It also helps to, a little bit, direct the light in. But then, it hits the lens, which directs it even further. But I get a little ahead of myself, because there's another part of the eye that allows more or less light to get in. And this is known as the iris. And there's common misperceptions about the iris. Because a lot of times when you see your eye, you kind of see that black dot in the center. And there's a lot of people that think that that's a black dot. But it isn't. It's a hole. And the best way to explain the iris is to explain a camera, an aperture, as it were. And on a camera, and if you ever come and see me at school, I actually have a camera aperture that I can show you, which I forgot to bring home with me, so sorry. But I have a picture that I'm about to bring up. The aperture is what kind of gets bigger and slower, or sorry, bigger and smaller on a camera to help let light in. And so, ooh, there we go. This is an example. Hopefully you can see. So you have a large aperture, and then it goes to a smaller aperture. And you can do this with a camera, and you know, the little hole that you can take a picture through gets bigger, and it gets smaller. And essentially what this is doing is when you have a large aperture, it's letting in a ton of light. And when you have a small aperture, it's letting in just a little bit of light. And that's how our iris works. Now another thing I'm going to attempt to show, and it involves me turning off the light, is an actual, if you've ever heard of the slow-mo guys, they do a slow motion of one of their eyeballs, going from a dark room to a light room. And it's to kind of see, again, our aperture, our iris getting bigger and smaller. And what's so interesting about this, and if you can't really see it on this video, again, this is just a trial. I will have it linked, or you can look it up yourself, it's slow-mo guys. But it shows that the iris is essentially just that opening. It's this muscle that gets bigger and smaller around the eye to let in more and less light. But let's see if I can do this. If it doesn't work, it doesn't work. Alright. So let me make it nice and big. And hopefully what you can see, again, I can't quite tell. But here's the eye, and this whole area right here, right now, is the opening of the iris. So this is just a hole into the eye. And then this area right here is kind of the iris, that muscle that'll get bigger and smaller. And what you'll see is that as the light gets turned on, because I believe it hasn't fully been turned on yet, though it might be, but you'll see the eye reacting to it, and that black hole getting smaller and smaller. The iris is contracting in a way to let less and less light in, because there's a bright light shining on the eye, which is damaging. And so, you know, you don't want to damage the eye, and so it lets less light in. But let's see if this can be seen. If not, I'll provide the video. Alright. So as you can see, hopefully, it's closing. And so this, getting smaller and smaller, and again, it's just an opening back of the eye. But you can see how it's stretching, getting smaller. There's a zoom in of it, where you can kind of see these openings, all those different fibers that stretch. So hopefully, you were able to see that. If not, again, I can provide a video. But what that's doing is, again, it's controlling how much light is able to come in. Thank you for helping me, Lucy. So this area right here, is the iris. And so it's all these little fibers, as you hopefully saw in that video, that contract and constrict to allow different amounts of light to get in. And then that amount of light that gets in then hits the lens. And what the lens does is it helps to angle the light so that it'll be in focus when it hits the back of your eye. Because the way the vision works is it's all sensed on the back of your eyeball. It's also upside down, which is very interesting, because as you'll see, what happens is the light comes in and it's flipped upside down. But luckily our brain is smart enough and it flips it right side up. Yes, okay. Little side fact for those of us with glasses. The reason why we wear glasses the majority of the time is that the way that this lens isn't quite bent the way it should be. It's too bent either this way or it's too bent that way. And so because of that, and depending on which way it's bent, by the way, determines if you're nearsighted or farsighted, or if you're lucky like me, you can have astigmatism, where it's just kind of all misshapen. And so what happens, the reason why you get glasses, is that light, before it even makes it to the cornea and the lens, the light already gets bent a little bit. So by the time it hits here and gets bent again, it'll be nice and crisp when it hits the back of our eye. That's why you have glasses. And there's ways that you can kind of test your own vision and figure out what kind of glasses you would need. But again, if you want to know that, take a physics class. But ultimately, again, all of these areas of the eye up here is all about angling that light, because again, it's coming from the outside world into us. It gets angled so it can hit the back of our eye. And so this is the retina. And the retina is what has all these different cells. But the ones, for the sake of this class, that you need to know about are the rods and cones. Because remember, those are a receptor, or they're sensory receptors. And so it hits those rods and cones. They take that light and essentially translate it. That's the way I'm going to describe it. Translate it into neural signals. Remember, neural pathways. And then it gets sent down what's known as the optic nerve, where it then goes, as you recall from last chapter, to the occipital lobe at the back of the brain, which is in charge of vision. One thing that's really interesting, though, is in the back, obviously, as you can see, all the nerves go down this optic nerve, but right here, where the optic nerve is, there's in fact one area that can't pick up on light signals, because that's where the communication cord is, essentially. So you can't have rods and cones there. And so we actually have a blind spot, as you can see here. And there is a way that you can find your blind spot. And all you need, if I can find it, because I just had it on my table, is a pen and a piece of paper. So what you do, and you can do this with a Post-it note, and this might be hard for you to see, so I'm going to bring it up. I'm also going to turn the lights back on. Is on your sheet of paper, you're going to put a plus sign on one side and kind of a dot on the other side. Again, I'm doing this a bit bigger. You want to do this on like a Post-it note, but it should look like that. There you go. Ignore that I'm writing this on a piece of paper that has writing. So a plus sign and a dot. What you then do is you cover one of your eyes. I'm just going to do this one, because why not? So you cover one of your eyes, you focus on the plus sign. You move it around, closer, further away, there we go. And eventually, staring at that plus sign, the dot will disappear from the paper. Again, you have to keep focusing on the plus sign, but in your peripheral vision, that dot will just vanish. That's where your blind spot is. It's more difficult for some than others to do. You might have to do your other eye. Feel free to pause this video and try it, or try it afterwards. But that's just showing the one area where, the light from where that dot is was sent back, but it hit a place that couldn't receive it. But we don't have this random gap in our vision. It doesn't affect us. When you look around, you can still see everything, because our brains are smart. It fills in those gaps. It says, okay, we were looking on a sheet of paper, and the sheet of paper was white. And so even though, we couldn't see this little area, it fills in the blank and says, oh, it must also be white. And so we see it as a white sheet of paper. There's been some instances of individuals that have bigger blind spots due to, damage to the eye, damage to all sorts of stuff. And again, the brain tries to fill it in. And so there was a case of someone that had a really big blind spot, and for some reason, their brain decided to fill it in with cartoon characters. And so they would see cartoon characters, which was really interesting. But it just shows just how amazing our brain is. But that's how vision works. You know, this is kind of a simplified version. But essentially, all the stuff up here is helping to redirect that light that comes in. So when it gets to the area that can translate it to a neural signal, it's nice and crisp. And I'm going to keep coming back to this when I talk about the senses. But what's so interesting about the senses and then your brain, that your brain can really your brain can only understand one language. And that's neurons and neural pathways. Your brain doesn't understand light. It doesn't know what that is. You shine a flashlight on your light, it's not going to sense anything. And so it's up to our sensory organs, like our eyeballs, you know, our skin, our nose, our ears, our mouth, our tongue, all of that. It's up to those to translate all the different languages from the outside world, you know, light and waves and all of that. Our sensory organs translate it into a language that our brain understands. And again, that sensation, it's receiving it and, you know, sending it to our brain. That's a sensation. And I believe it shows in more detail on the next slide. Yes, it comes in, goes through the fovea and all of that. This is kind of, again, this is the back of the eye, as you can see. So the retina, this is a zoom in of that. So again, you have that optic nerve. So this would be where your blind spot is. This is the light that hits it after it's been nicely, you know, redirected. And these are all the different things. We have ganglion cells, bipolar cells, and then the rods and the cones. And again, rods and cones, rods are essentially, let's see, you know, black and white, light and dark sort of thing, and then the cones are color. And so it takes that information, translates it to those neural signals in a sense, and then it gets sent down the optic nerve to your occipital lobe. Yes. And then this, again, you'll see it in your slides, and I'll talk about it in more detail. Color vision, though, is interesting. How do we see colors? How does that work? And there's actually different theories. And what's so interesting, and you'll see this for some of the other senses, is it's not that, you know, one theory is right and the other one's wrong. They both kind of explain it. And I'll show you what I mean. So the first one is the Trichromatic Theory. And this is the whole idea that there are three colors, three primary colors. Now don't confuse this with the primary colors in art. The primary colors in vision are green, kind of a blue-violet, and red. And the whole idea is that these different combinations are what we see. There's a wonderful video. I might see if I can find it, but if not, you can find this by Vsauce, where it says, and unfortunately I don't think the color's on here, but if you ever see the color yellow in, you know, on a computer screen, you're not actually seeing yellow, as it were. Because all of the screens, so of course it might be different with technology and all of that, but within a screen it's made out of pixels. And if you were to zoom in on this screen, you would see teeny tiny little pixels that are comprised of green, blue, and red. And then whether in what combination those colors are shown, you then see all the different colors. You see yellow, you see black, you see white, you see everything. And so this is the Trichromatic Theory. Again, trichromatic, three colors. There's all of these combinations firing that then allow you to see all of the different colors out there. But it's just those three. That's one of the theories, and again, we see it. That's how TV screens work. It's just pixels that show those three colors, and those three colors only. But then we perceive all the other colors from them. Well, that's not the only theory. We then have the opponent process theory, which is the whole idea that when you get to the rods and cones in your eyes, they have, when they're firing, one color, and when they're not firing, the other color. So you have red, and then the opponent to it is green, blue, and the opponent is yellow, black, and the opponent is white. And so the whole idea is that, you know, when you see a certain color, again, certain ones are firing, certain ones aren't, but then when it's firing, you see one color, and when it's not firing, it's the other color. And essentially how we know that this works, and I know that this is on the exam, evidence of this theory is what we call an after image. And to show what that is, and I don't know if it's going to work on this video, but hopefully it will. If not, you can download the PowerPoints and do it on there. But what I'm going to need you to do, and I'm going to make sure to be off of the screen, is you need to stare at that black dot in the middle of the flag. And do not take your vision away from it. If you can, try not to blink, but just stare at that black dot. I'm going to have you staring for just a little bit more. This works best in kind of a darkly lit room, but we're going to see if this works. So you're staring at that black dot, not looking anywhere else, staring at that black dot, trying not to blink. And then, see what you see. Now, if this worked, you should be seeing a red, white, and blue flag. Again, this might not work on this screen. Hopefully it did. But if you did see a red, white, and blue flag, this is an example of an after image. Because the whole idea, and I'm going to go back to it, is when you were looking at this flag, you were seeing the yellow and the green and the black. And if you recall, those opponent colors to that are red, white, and blue. And so while you were staring at this really intently over and over and over and over and over again, you were exciting those parts of your eye, and the rods and the cones, I should say. And so when finally it went to just kind of a neutral screen that was white, your eyes, those rods and cones were like exhausted. And so instead of it just going back to neutral, just going back to white as what's actually there, it showed the opposite of those colors because it was kind of still recovering. And so you saw the red, white, and blue. And again, this might not have worked in this video, but I can guarantee it does work. I've done this in my class every time, and everybody sees it, and then if you blink, you can kind of see it for a little while later. Don't worry, it's not permanent. But that's an after image, and so it shows that that also works. But if you recall what I said for the trichromatic theory, we know that works because that's how computer screens work, and that's how TV screens work. And so both of these theories, both the opponent processing and the trichromatic, explain color vision. So it's not really just like in psychology, it's not that one thing's the answer and everything else is wrong. It's more that they both kind of complete the picture. Ooh, this is another thing. There's something known as colorblindness. And it's not always, just seeing in black and white. You have monochromites, dichromites, and trichromites. I believe is how it is called. Yes. And so if it's mono, that means you can only see one thing, so it's a black and white. If it's dichromats, that means that it's struggling with, if I recall correctly, the green and the reds. And so if you're a dichromat, you wouldn't be able to see, and again, this might be harder on this screen, but again, see it on the PowerPoints, you might not be able to see the red triangle in these pictures. If you see the red triangle, congratulations, you got the full trichromat, you can see all three. But a lot of times when people think of colorblindness, they think, oh, they can't see any color. And that's not true. So this is just an example. And there's different theories as to why there's color blindness. It can be damage to different parts of the brain, it can be damage to the eyeballs, there's all sorts of things. And this is just a way to test it. And that's essentially it for vision. When we come back next, in the next module, we will then be talking about the next kind of big sense, because again, the way that you are hopefully learning, hopefully you are learning, the way you're learning about all of this is not only through seeing this video, but also hearing this video. So a lot of times that vision and hearing are kind of those two really important senses, especially to learning, though of course there's many, many other ways. So we've already talked about vision, and in the next module, we're going to talk about hearing, and then get into kind of some of those other fun senses, because if you recall, as I said, there's more than just